Hello everyone, welcome to today's lecture on quantum supremacy. This is for the course LABMP 590. And so today, this lecture, we have a few objectives that I really want you guys to take home from. The first one would be understanding what it means, what the word quantum supremacy means. The second one is to understand all the basic concepts that are encapsulated by quantum mechanics. After that, I want you guys to be able to brainstorm and envision possible applications of quantum mechanics and what those applications might mean for society. After that, you guys should be able to differentiate between quantum mechanics and classical computing. And after that, we can talk about the ethical concerns and implications quantum mechanics might have on quantum computing and how the concept of quantum supremacy might affect our society. Okay, let's talk about quantum mechanics. So the dictionary definition of quantum mechanics is that it's a branch of physics that deals with the mathematical description of motion and interactions of subatomic particles. Now, these concepts encapsulate concepts like the quantization of energy, wave-particle duality, the uncertainty principle, and the correspondence principle. So now let's talk about the importance of quantum mechanics. Okay, so like any scientific concept, its goal is to explain phenomena of the world that isn't quite able to be explained by the current concepts. And so in this case, quantum mechanics helps explain phenomena that classical physics was never able to explain. And so the applications of quantum mechanics becomes evident when you talk about technologies in optics and electronic components. And there's no better example than in computing. Okay, here's a great diagram that can help us visualize just the breadth of applications when it comes to quantum computing and quantum mechanics rather. So on the very right or on the very left, we have MRIs. Further on the very right, we have lasers and telecommunications. And then we have atomic clocks and GPS. You might not see the relation there. And finally, of course, we have computers, smartphones, so quantum computing. So I'm going to go into specifics of every category. Okay, so MRIs, which stands for magnetic resonance imaging. If you guys have taken any organic chemistry courses, this is the same technology they use to obtain NMR spectra for organic compounds. And so MRI is a great example of how quantum mechanics can be applied to medical diagnostics. This is now a staple in medicine. And so how it works is it applies the basic principles of quantum mechanics to measure the hydrogen content of our body tissues. And so this machine applies a magnetic field to our body, and this magnetic field initiates nuclear flip changes in the hydrogen atom, and we can measure this nuclei flipping and get the concentration of hydrogen atoms in our body tissues. Now this is especially relevant when we talk about the soft tissues of our body, because X-rays are great at detecting our hard tissues like bone, but they become overexposed when we measure the soft tissues. And this is why MRI has great applications in measuring soft tissues, in visualizing soft tissues rather. Okay, the next application is lasers. So lasers were basically envisioned by Einstein in his 1917 paper on radiative emission. And so most people don't know this, but laser is actually an acronym, and it stands for light amplification by stimulated emission of radiation. I think we all know that staring at a laser light isn't bad. Staring at a laser light is really bad for our eyes. Now, if you've taken fundamental or sort of basic just physics, you know that the energy of light is determined by its wavelength, right? So red light is a very long wavelength and low frequency, whereas something like a blue light would have a very high frequency and a very small wavelength. And so the blue light has more energy. And so you might be wondering, like, we can see laser light all the time, either a red pointer or those green pointers. So how come they still damage our eye, even though like red light shouldn't be damaging? Now it comes down to the word here, amplification. So lasers, they amplify monochromatic light. And so the power density of the light is very high, even though we can see that wavelength of light. And so when that laser light hits our retina, it actually has more power density than staring at the sun, which is why the keyword amplification there. And so we can see some applications of lasers where monochromatic light is really useful for our barcodes, but also for telecommunication. So as crazy as this sounds, the majority of our internet infrastructure is actually made up of huge cables underneath the sea, underneath the oceans, the Pacific Ocean and Atlantic Ocean. So as advanced as our technology is, it's still run by huge, gigantic cables under the ocean. And these huge, gigantic cables that are meters in diameter are all just protection for this very, very thin wire of fiber optics, which is laser light. And so this is where the applications of quantum mechanics come in for internet and phone lines. Okay, now let's talk about GPS and atomic clocks. So I think we learned at a very young age that GPS, the Global Positioning System, relies on 3 satellites that help us triangulate our position. And so the 3 satellites are useful because our distances between those satellites are different, where satellite A, B, and C will have different distances between us. And it's that different distance that allows us to triangulate our exact position. And so it does this by measuring the time of arrival for the speed of light. Now, fundamental rule of physics is that light travels at a constant speed, which is 300,000 kilometers per second, or 1 foot per nanosecond. Now, knowing how fast light is, the minute differences in distance between us and different satellites is super small. If we had a stopwatch and we timed the speed of light to each individual satellite, we would get the same time every time. So that wouldn't really help us differentiate our distances between the satellites. And so we need atomic clocks, which have super high accuracy and precision, which allows us to detect the smallest change in time of arrival for the speed of light. In this case, our satellites use radio waves, which is a form of light. And so atomic clocks utilize quantum mechanical principles, which is where it measures the oscillation in microwaves emitted by cesium atoms, or sometimes rubidium atoms. And this oscillation is super precise and accurate, and this is why atomic clocks become super useful in our GPS systems. Okay, now we can talk about computers finally. So this slide is just talking about classical computing. So in classical computing, we're mainly talking about the CPU, so the central processing unit. And so in the CPU, it runs on information that's encoded in binary digits. So this binary means yes, no, or 0, 1. And so this is where the word bit comes from, because binary B and digits the IT, so bits. And so composed of these zeros and ones, they form what's called a bit. However, this bit is super small information, and it wouldn't be efficient to use this kind of information. So they're encapsulated into what's called a byte. So 8 bits would make a byte. And that's just an image of a supercomputer. And here we can see how letters can be converted through standards, international standards, which give us the binary values of every letter. So now we can talk about quantum computing. And so quite the opposite to classical computing, quantum computing uses quantum bits or qubits. And these quantum bits or qubits have a very unique property in that these bits can exist as 1 and 0, or exist simultaneously as 1 and 0. And so this is an excellent example of the concept of superposition, which is where an entity can exist in multiple states at the same time. Now, depending on the quantum computer, they'll be measuring either an atom or a photon, an electron, or an ion, depending on how that quantum computer was designed. Now, these entities can actually have another quantum mechanical property, which is called quantum entanglement. Now, what that means is entities, no matter how far they're separated, when they're entangled, their states will correlate with one another. So if we're talking about an electron that's spinning up, this electron that's also entangled with it will also be spinning up. When this one spins down, this one will also spin down. So that's the concept of quantum entanglement. Now, these quantum computers, they look very interesting. They certainly look very different from our laptops and computers at home. And that's because they actually have to be cooled right down. So quantum computers have to be cooled down to minus 273 degrees Celsius. And the reason we have to cool them down that much is because for these entities to exist in these superposition states, they have to be kept very cool, and that helps stabilize them. If they're not kept that cool, they'll collapse down to a single up or down, and they won't be demonstrating that superposition that we need. And so, just quickly to summarize how these quantum computers actually work. So for classical computing, they solve problems sequentially, which means that they don't really multitask. So when you have a task at hand that requires multiple steps, they can only do every step one at a time. Whereas quantum computers, they do all the steps simultaneously all at once. And so how that works is qubits, which are the bits of the quantum computer, when they're cooled right down, all of them are spontaneously and simultaneously undergoing their own superposition. So they're either flipping up and down, 1 or 0 at once. And so the correct answer is when all these qubits interfere constructively because they're all entangled. So imagine this huge box of qubits floating in space, and they're interacting with one another under their superposition states because they're very cold, they're very stable. Now, you know in quantum mechanics, the moment you observe an entity, it collapses down to a single answer. Now, we don't want that. We want them to be constantly flipping back and forth. And so the quantum computer's job is to urge and encourage these qubits to form a constructive pattern. What that means is the moment we observe it under its constructive pattern, it is more likely to collapse down to the right answer than the wrong answer. So that's the basic idea of how quantum computing works. And so now finally talk about how it will reduce power consumption. So there's two ways it does that. The first way, which is not so obvious, is that we're cooling down these computers to minus 273 degrees Celsius. Now we know that means it's going to take a lot of energy, whereas our laptop, we can just plug it into the wall. So how is this being power efficient? The way it's being power efficient is because when it solves these super hard problems that require immense amount of multitasking, you would need like 50 million laptops to achieve the same result than just cooling down one single quantum computer down to 273 degrees Celsius. The other way is that quantum computing utilizes quantum tunneling, which makes the energy usage down by 100 to 1,000 points. Okay, so now we can talk about the similarities and differences between classical computing and quantum computing. And so right off the bat, the most obvious example is that classical computers use binary bits, so that's 1 or 0, yes or no. And then quantum computing uses quantum bits or qubits. And these qubits can be either 1 or 0 or 1 and 0 at the same time. And so another thing I want to touch upon is that between the differences is that classical computing, normally when you buy a laptop or a computer, the processor is advertised in two ways. The first way is its core count, which could be a dual core or a quad core. And then the other property that we talk about, the CPU, is the processing speed, which is normally defined as the gigahertz, right? You can say it's like 4.6 gigahertz CPU. What that means is its frequency or its clock speed, which is how many cycles or how many tasks this CPU can perform at a single time. Now, they're not performing the task at the same time, they're performing it sequentially, so one after the other. So when we talk about a CPU that has a 4 gigahertz processor, it means it can perform 4 billion tasks in 1 second. 4 billion tasks not at the same time, but 4 billion tasks one after another in a single second. Whereas in quantum computing, there's not really an equivalent to its processing speed. It's like comparing apples to oranges a little bit when we talk about processing speed. Because in quantum computing, it doesn't perform the task one after the other. The equivalent would be it performs 4 billion tasks at once. So with 0 time, it performs it all at once. And so that's really the key difference. So for single tasks, like when we're browsing social media, we're watching a video, we're playing games, the speed of how many tasks can perform at once matters way more, and that's why it's better to use classical computing. Whereas for industrial purposes or research purposes, when we're trying to analyze massive amounts of data, we're trying to run simulations on weather or simulations on protein folding, that kind of computing is less about how fast we can process that data, but rather because the data is so immense and there's so many variables happening at once, it's that we need to be able to hold and represent all these variables at the same time, rather than sequentially one at a time. And so that's where the applications of quantum computing really comes into play. So now we have a great video to demonstrate and help explain what quantum computing is.
Quantum physics, one of the most successful theories of modern science, describes the way our world works at the most fundamental level. Quantum computing has become one of the leading applications of quantum physics. Quantum computers have the potential to solve some of the world's most complex problems that are beyond the reach of even today's most powerful supercomputers. Quantum computers are not going to replace classical computers, but their radically different way of operating enables them to perform calculations that classical computing cannot. Let's see how they differ. Classical computers encode information in bits, and each bit can represent a 0 or a 1. These zeros and ones act as on-off switches that ultimately translate into compute functions. To perform a simple calculation, like solving a maze, a classical computer would test each possible route one at a time to find the correct one. Just as classical computers have bits, quantum computers have qubits. Qubits, however, make use of two key principles of quantum physics: superposition and entanglement. Superposition means that each qubit can represent a 0, a 1, or both at the same time. And entanglement happens when two qubits in a superposition are correlated with one another, meaning the state of one, whether it's a 0, a 1, or both, depends on the state of another. Using these two principles, qubits can act as a much more sophisticated version of switches, helping quantum computers solve difficult problems that are virtually impossible using classical computers. To illustrate how this makes quantum computers more powerful, let's look at some numbers. Take a classical n-bit computer, with n representing the number of bits. It can represent and examine only one system state at a time. An n-qubit computer, however, would have the power to represent 2 to the power of n system states and perform parallel operations on all those states at once. This means that every time you add just one more qubit to a quantum computer, the number of states it can represent and examine doubles. So a 50-qubit quantum machine could examine 2 to the power of 50 states at once. This exponential increase in power, together with the entanglement of qubits, is what allows quantum computers to solve certain problems so much more efficiently. While a classical computer solves a problem like the maze by testing each possible route one at a time, a quantum computer uses its entangled quantum states to find the correct route quicker, with far fewer calculations. Think of it this way. Technologies that currently run on classical computers can expertly find patterns and insights buried in vast amounts of existing data. But quantum computers will deliver solutions where patterns cannot be seen because sufficient data does not exist, or the possibilities for discovering an optimal answer are too enormous to ever be processed by a classical computer. Quantum computers could lead to the discovery of new medicines and materials by helping us untangle the complexities of molecular and chemical interactions. They could help the financial services industry make better investments by finding new ways to model financial data and isolate key global risk factors. They could even transform supply chain and logistics by finding the optimal routes across global systems, like optimizing fleet operations for deliveries during the holiday season. Quantum computing won't replace our everyday computers and smartphones, but its ability to solve complex problems will open up a new universe of information, transforming our view of the world and the way we navigate it.
Okay, so that was quite a good video. Now I want to talk about the concept of quantum supremacy. Okay, so quantum supremacy sounds like a crazy hard word to understand, but it comes down to a very simple idea, which is that this concept or word means and helps describe when a situation, this task, is performed much better with a quantum computer than a classical computer. So in reality, technically, a classical computer can do everything a quantum computer can, but we gotta talk about practicality. So when it's not practical to use a classical computer to solve a problem, where a quantum computer solves it much better, that's when we can say, in this situation, there's quantum supremacy happening. Okay, we can talk about the quantum race here. You can see where in the world right now, how much money is being spent on the research for quantum computing. So in the world right now in 2015, it was basically 1,500 million euros being spent on the world. And these red dots just show specific regions in the world. And what we see is like basically the entire world is basically engaged in this effort, in this quantum race, if you will. And what people are really enjoying with this quantum race is that it's not really between countries, but rather between large organizations like Microsoft and Intel and IBM. Okay, now recently Google, they released a video and talking about how they might have achieved quantum supremacy, which again means where a supercomputer performed better at solving a problem than a classical computer ever could. And just a quick summary of what exactly happened was that Google created this artificial problem, which was this huge network. And what they did was they let the quantum computer solve this network, and then they let the classical computer solve this network. And if both computers solved it at around the same time, they would increase the difficulty of this network. So they increase the complexity of this network. And then they'd run the experiment again. And so eventually, at the start, of course, classical computing was doing it better than the quantum computer. And so they keep increasing complexity, and slowly the quantum computer was able to perform this complex network much better than the classical computer ever could. It came down to a point where this network could be solved by the quantum computer in 200 seconds, whereas they would estimate it would take the classical computer to solve this problem in 10,000 years. And so IBM, they criticized their experiment because they said that this problem favored quantum computers more. It had a bias towards it. Now that's inevitable because as you increase the difficulty or the complexity of a network, what matters more is how many tasks you can do simultaneously rather than how fast you can do the tasks. And so here's that video. Here's what Google said basically.
The tantalizing promise of quantum computers is that they can do certain tasks exponentially faster than classical machines. And the quantum supremacy experiment is proof that this is indeed the case.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
The classical bit stores information as a 0 or 1, and a quantum bit can be both 0 and 1 at the same time. If you have 2 quantum bits, then there are 4 possible states that you can put in superposition. With 3 qubits, it's 8, 4 qubits, it's 16. It grows exponentially.
The nice thing about quantum supremacy is that it is a very well-defined engineering milestone.
In a nutshell, what we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
To actually demonstrate quantum supremacy, we have these 3 steps. First, pick a circuit. Second, run it on the quantum computer. Third, simulate what the quantum computer is doing on a classical computer. We gradually increase the complexity of that circuit. At some point, it becomes completely impossible for the classical computer to keep up. Then we say we've achieved quantum supremacy.
We started building together the quantum chips to do this experiment. And then the evolution of the devices with more and more qubits and more complexity. It's very much an iterative process.
A lot of the work that we put in was not just these chips, but is also the infrastructure that you need to drive those chips. The cryostats that we install them in, all of the control electronics, software, all of this stuff is needed, and it all has to be developed.
When the experiment started, we were getting data from the experimentalists. We saw initially a beautiful straight line corresponding to our predictions.
Then, right before we hit supremacy, it dropped much faster and it fell below the threshold where it needed to be.
And there's nothing we can do because we don't know how to analyze past that. So everyone's like, oh, we're screwed because it's getting really, really bad at large number of qubits.
It's like, well, maybe there's some really complex interaction between all the qubits.
It turned out that the reason was rather benign. We calibrated a little bit better and then this problem disappeared.
So there wasn't like a, oh, we did it. I think we crossed it, and then it wasn't clear that we crossed it, so we crossed it a little bit further.
It took me like a day to realize, like, hold on, this is actually experimental data. It's kind of amazing to see, how well the theory works.
The processor that achieved quantum supremacy is called the Sycamore processor.
And it's parallel processing 2 to the 53 states, which is 10 million billion. And thus that enormous amount of parallel processing is what gives it the power.
When we run small chunks of the computation in the largest supercomputer in the world, our estimate is that it will take thousands of years to complete the full computation.
Technologies are born this way. Let's say the space age started with a satellite orbiting Earth, and it was not doing much, it was just beeping.
The big technical achievement of quantum supremacy was really dependent on all this young talent who's kind of taken this and gotten it to work at a very technologically capable level.
We have reached a new computational capability. There are certain computations, the only place in the world where you can compute those things is here in our data center at Google Santa Barbara.
For the first time, we're showing that we can solve a problem that is just infeasible to do on the biggest computers ever made by civilization.
And what's exciting is now we're ready to turn this over to the world and say, let's figure out what we can do with this.
The thing that excites me most is building a useful quantum computer. When we can give a researcher a tool that is unlike any other and say, great, figure out something cool to do with it. Mankind is pretty good at that.
Okay, so Google showed a huge and crazy example of the possibilities of quantum computing. So now we can talk about ethical concerns involved with quantum supremacy and quantum computing. And the first one is, what does it mean for us? So as you know, every single day, every single year, technology has a greater impact and role in our lives. It's inevitable. We all have smartphones. There's almost no task we can do better than a computer can. And so classical computing is very phenomenal technology. And now we're adding in another aspect, which is quantum computing. So what does that mean for us? And so now let's talk about privacy. Now I haven't really touched upon privacy, but it's a big deal when it comes to quantum computing. So when we talk about privacy, we're talking about encryption keys. So when you have a password for any website, it's basically encrypted by a 256-bit AES encryption standard. So the whole world uses this standard. Now, you may be wondering, if the whole world is using this standard, how is it secure? It's secure because to solve this encryption key, it just wouldn't be feasible for a classical computer to do so. So a classical computer, again, performs tasks sequentially, one at a time. If it were to try to solve someone's password, it would have to try every single password combination one at a time. What that means is if this password is 16 digits long, that'd be 2 to the 16 possibilities. Now, any computer can't perform that many password checks. It would take years, like years and years to solve this password. So it wouldn't be practical. When we talk about a quantum computer and its qubits, its ability to multitask is defined by the formula 2 to the n, where n is the number of qubits. And so the most bog standard quantum computer these days has 50 qubits. So it can perform 2 to the 50 problem-solving events at once. And so that's a large number of passwords it can perform and check at once. So it doesn't have to check one at a time like the brute force method of classical computing. It can perform all the password possibilities in that instant. So that makes none of our passwords secure. Now, who really cares about our laptop password? This is concerned with our password for our emails, our banking information. Basically, none of our passwords become safe then. Another example of privacy is when it comes to cryptocurrency. So right now, the most common one is like Bitcoin and stuff. And the way these currencies hold their value is because every currency is encrypted with a 2048 RLS encryption key. And so it's been proposed that you would just need a quantum computer with 4,000 qubits to solve this encryption key. Now, this is horrible because, in fact, a lot of the world's economy is actually now represented by the crypto market. And so what does that mean for our economy? And so now we can talk about the fear of quantum computers falling into the wrong hands. Now, right now in the infancy of quantum supremacy, only the large companies that have massive funding, sometimes federal funding, can actually build these quantum computers and have the know-how of how to how to use these quantum computers to solve these problems. And so if these companies have that power, then they also have that power to kind of they also have the power to know everyone's password, and basically no one is truly safe now if these huge companies have that kind of power. So that's what it means by falling into wrong hands. Now, the next point is talking about when quantum supremacy matures. It matures in such a way that now quantum devices are ubiquitous. Everyone has them in their pocket. So now what does it mean when everyone is able to unencrypt anyone's password? Now it's been proposed that as the quantum computer, as it matures, as quantum supremacy increases, so too will the landscape of our security. So people propose that they'll both rise at the same time. So no one will really know about that. Thanks so much for listening to this lecture. I hope you learned a lot from this. Here are the references.